Welcome to the show, Ramanujam Life and Legacy. Srinivasa Ramanujan, a world-famous mathematician, was born in 1887 on December 22nd. And in India, we celebrate this day, December 22nd, as National Mathematics Day. Unfortunately, he died young in 1920. This is the 100th death anniversary year of Srinivasa Ramanujan. In this year, Vigyan Prasad is conducting a year-long program to pay homage to him and popularize mathematics. This show is part of that Ramanujan Yatra 2020. Ramanujam, Life and Legacy. In this show, we are going to be joined by Professor R. Ramanujam of Institute of Mathematical Sciences, Chennai, and Professor A. Raghuram from Indian Institute of Science Education and Research in Pune. So let's start this conversation, and perhaps I would begin with Dr. Ramanujam. Life of Ramanujam is full of very interesting incidences, anecdotes, which are lesson even today. If I ask you one incident from Ramanujam life that sticks in your mind, what would you say that as?
Well, there are many incidents, but about when we think about the life of Ramanujan, maybe I'll talk about incidents later. But I want to talk about his life.
Mm-hmm.
The fact that he was a mathematician who developed his love, cultivated his love for mathematics single-handedly, in total isolation. As a child, a quiet child, kept to himself, and a child sitting and trying to find the value of pi to any number of decimal places, and this is something that grew into a very deep love, and he would later on connect computations of digits of pi to modular forms, which had a great impact. So that is something to keep in mind. I mean, and also in poverty. I mean, Ramanujan suffered. We talk a lot about Ramanujan. He's a very romantic figure, but it's also important that as he grew, he had very little. In fact, when he went and met the Nellore collector, and then he says, "Look, all I want is something for 2 meals a day and to buy paper." So this is, I think, important to think about. And then the great episodes of his life that we keep talking about, when he wrote a letter to several British mathematicians, and then in particular the letter to Hardy, that single letter containing 120 theorems listed, which stirred Hardy. But more than that, simply as a piece of mathematics written, that letter is, I think, astonishing. I think I would.
Yeah, that's a really wonderful. Perhaps I think because we are talking about Ramanujam, I think it's important that we also talk about his mathematics. Of course, many of his areas of work are too involved for most of us to understand that easily. But however, one aspect of is mathematics, which perhaps we can have a glimpse into, is the area called as partition function, for which he is very famous. Maybe I would ask Professor Raghuram, can you explain to us what is this partition function? What did Ramanujam do in this partition function? What did he find? What's so important about it?
So, first of all, thanks for having me, TVV. So Ramanujan's work on partition functions, this is probably his work with Hardy, which is the most famous piece of his work. And certainly it's his most cited paper for sure. This was published in 1918, if I remember correctly, in Proceedings of the London Math Society. It's called Asymptotic Formula in Combinatorial Analysis or something like this. So, okay, what is partition? partition, it's a very, very simple thing, which even a schoolboy can understand. You take a number, a positive integer, a whole number, like say 3, and you want to know how can I break up 3 into smaller pieces. I can write it as 1 plus 1 plus 1 or 1 plus 2 or 3 itself. So, and then if you wanted to do this for the number 4, then you realize that there are 5 ways of breaking up 4 into smaller pieces, smaller integers, positive integers. And very quickly, if you play around, you will see that the number of ways in doing this shoots up very, very quickly. So already for the number 10, there are more than 40 ways. If I remember correctly, I think it's 42 ways of writing 10 as the number of partitions of 10. And if you go to 50, it's like 2 lakhs, more than 2 lakh ways. And if you go for 100, it's several million, maybe close to 200 million ways of writing 100. So the number of partitions of an integer n grows very, very rapidly. And why study partitions? Well, of course, it's a very basic question to ask, partitions, but then it happens to be very important in physics. It goes into statistical mechanics, but all this is after the fact. Ramanujan studied it simply for its intrinsic beauty, I would say.
Let's just take a second. So what we'll do is that we'll play a small audio visual, which will try to explain that how the partition number for some of the smaller numbers work. And then we'll be able to see that how the number of ways that you can partition them is keeping on increasing. We'll take a look at this AV and then come back.
What is partition functions? Let's take number 2. How many ways can you write this as sum of smaller natural numbers? In the simple case of 2, 2 is equal to 1 plus 1, 2 is equal to 2 plus 0. It means we can partition 2 in 2 different ways. What about 3? 3 is equal to 1 plus 1 plus 1. 3 is equal to 2 plus 1. 3 is equal to 3 plus 0. In the definition of partitions, the order does not matter. 2 plus 1 and 1 plus 2 are the same partitions of 3. This is how we can partition 3 in 3 different ways. Before you hasten to conclude 5 can be partitioned in 5 different ways, you must know in fact 5 can be partitioned in 7 distinct ways. 5 is equal to 5 plus 0, 5 is equal to 4 plus 1, 5 is equal to 3 plus 2, 5 is equal to 3 plus 1 plus 1, 5 is equal to 2 plus 2 plus 1, 5 is equal to 2 plus 1 plus 1 plus 1, 5 is equal to 1 plus 1 plus 1 plus 1 plus 1. Mathematicians write this into a notation: partition of 5 equal to 7. Partition of 0 equal to 1, partition of 1 equal to 1, partition of 2 equal to 2, partition of 3 equal to 3, partition of 4 equal to 5, partition of 5 equal to 7, partition of 6 equal to 11, and so on. Can you guess partition function of 20? One may think that it may be something like 50 or 100 or say 200, but one can partition 20 into 627 distinct ways. Any guesses for partition function of 90? It is 566,341,73. As the number increases, the number of ways it can be partitioned show a surge in a mind-boggling way. The number of partitions of natural number series can be written as a series. The partition function is this. Though seemingly elementary, it is very difficult to calculate partition of n as n grows larger.
That was very, very, very interesting that how in this AV we can see that the number of ways the partitions were increasing when the numbers are increasing. Now let's go back to Professor Raghuram. You were explaining what Ramanujan was working on it. Please continue.
So the question is there a formula for P of n? If P of n stands for the number of partitions of n, is there a formula? And it was expected that having a closed formula is just maybe it's not possible. The next best thing is can we have an asymptotic formula? So what does this mean? This means some kind of a formula of of the variable n such that P of n and this formula get closer and closer as n gets larger and larger. That is the meaning of an asymptotic formula. And Hardy and Ramanujan proved the best asymptotic formula for P of n. and it is roughly of the order of each. It's an exponential of the square root of n, roughly. I mean, there's a far more explicit formula. And in this, proving this formula, so you see Ramanujan already had insights about this kind of a formula by the time he got to Cambridge. He had started working on a certain method, which now goes by the name Hardy-Ramanujan circle method. So not only the formula, but also a certain methodology, which is now a standard in the toolkit of an analytic number theorist, goes in this very beautiful and most cited paper of Hardy and Ramanujan. It's
that's interesting. And I also think that there is some connection between number 5 and number 7 with this partition
Yes,
number, right? Yeah.
Indeed. So, so one is the asymptotics. The other is what the buzzword is congruences. So here comes Ramanujan's genius. So just by looking at some simple values of P of n, he had this genius for manipulating series, infinite products. And so he made certain observations and he proved some of them. So I think closer to the time he passed away, 1919, there's a paper in the Proceedings of the Cambridge Philosophical Society where he proved the Ramanujan congruences, that the first one is P of pi n plus 4 is always divisible by 5. What does this mean? So take something like, say, 24. Or I already told you P of 50 is like more than 2 lakhs. So take a number like 54, and P of 54 is divisible by 5. Now, if you want to sit down and first of all compute what is P of n, and then this is divisible by P of 5, very quickly it gets beyond this kind of by hand computational capacity. So Ramanujan's genius was seeing this kind of divisibility properties coming from his ability with his genius for manipulating infinite series and infinite products. The partition function is nicely packaged into a certain generating series, which is what Ramanujan, that's what he played with.
This is why Professor Raghuram will play a very small AV to explain the divisibility by 5 and 7. We had already worked out some partition numbers for some numbers, right? So let's look at them and how they are divisible by 5 and 11. Let's take this AV and then continue this conversation.
Can you find any pattern? They appear arbitrary. Sure, our high school mathematics is not enough. The insight of Ramanujan is called far. Look at this series, in particular the numbers which are in bold. They are partition of 4 equal to 5, partition of 9 equal to 30, partition of 14 equal to 135, partition of 19 equal to 490, partition of 24 equal to 1575, partition of 29 equal to 4565. All these numbers 5, 30, 135 and so on are multiples of 5. The numbers 4, 9, 14, 19, 24, 29 and so on also have a pattern. These numbers can be written as 5k plus 4. That partition of 5k plus 4 is always a multiple of 5 for any number k. Ramanujan went a step further. He also showed that partition of 7k plus 5 is always a multiple of 7 for all k. Partition of 11k plus 6 is always a multiple of 11 among these papers. All these three patterns are called as Ramanujan congruences on partition functions. Though congruences do not reveal the exact value of partition of n, they give number theoretic information on the exact value.
We saw the audiovisual where we were looking at the numbers, partition numbers, and then how it is divisible by 5 and 7. Let's go back to Professor Raghuram. Continue, Professor Raghuram.
So there's a nice little story to mention here. So in these Ramanujan congruences, especially for the prime 11, he proved, he guessed initially and later proved that P of 11 times n plus 6 is divisible by 11 always.
Okay.
And this was not there in his first paper. And later, in 1921, his first paper on congruences. In 1921, which is after he passed away, there was a paper written by Hardy in the name of Ramanujan, published
Okay.
posthumously in Mathematische Zeitschrift, where Hardy has sat down with his notes and Ramanujan's notes and has ironed out a proof for the congruence for 11. It's a very nice and very first page of this paper. I've recently looked at it, and you feel sad. I mean, there is great beauty in the mathematics, and you feel so sad that this person, he passed away so early.
That's a really very sad stuff. I mean, of course, it's a part of the mathematics lore that suppose if he was alive and not died in 1920, what would have happened? But even then, I think his life has made a important impact. Professor Ramanujan.
Yeah, I wanted to add to what Professor Raghuram was talking. This ability of Ramanujan, especially in the Hardy-Ramanujan collaboration, to come up with ideas, deeply profound ideas that last, make lasting impact, is something astonishing. And Ramanujan had this. I'm thinking of something that has impacted areas like combinatorics and theoretical computer science, far away from the world that Ramanujan inhabited. And this is also another of Hardy-Ramanujan, what they call the normal order method. I mean, the question is something very simple. If you take a random natural number, how many factors would it have?
Okay.
Right? I mean, this is something that again a school child would ask, and they show that it usually has about log and prime factors. And this idea and the technique led to a whole field. Raghuram can tell us about probabilistic number theory, but as I said, which was developed by Erdős and other people, but it has had enormous impact in areas like theory of computation, algorithms today. This kind of probabilistic method, I mean, it's a method that really counts, right, in these things, and that inspires many people to come, and probably more areas will develop as we go along. So this ability that in every piece of work, the footprints are, some things that are far-reaching. Another thing that it reminds me of is monstrous moonshine. I mean, the very term is fabulous, right? I mean, it's something about a monster group, and that Conway and Norton did, but really inspired by Ramanujan's work and taking on from there, and that led to other very important mathematics again. So this idea that every work, every idea had a legacy, right? That would have far-reaching impact. This is typical of Ramanujan and his work, and the Hardy-Ramanujan collaboration, Rogers, these types, especially.
Even on partition function, for example, you can see in his first notebook itself, he was trying out partition numbers calculation. First notebook is essentially even before he left for Cambridge. Some of them were even done during his school days and early college days. I mean, so that is something very impactful and exciting, right? Yeah. That's a interesting part. I mean, one can even see that how you have been hardworking. I mean, as Professor Raghuram pointed out. Let me move on to one more question, Professor Raghuram. I mean, I'll start with you, and I want to ask both of you. Once American Mathematical Society Journal published a paper which said that 10 beautiful formulas of Ramanujan. I mean, beauty is connected with mathematics. So, if I ask you, Professor Raghuram, what would be in your mind the most beautiful formula of Ramanujan? Your pick.
Oh, this is a very difficult question. Mathematics is just loaded with beauty all over. But my particular favorite definitely goes to his 1916 paper called On Certain Arithmetical Functions. So this particular paper has, again, a whole lot of fantastic looking formulae, but there is one in particular. He studied a certain series, a certain, it looks like summation, some number power of n times q to the n, q is from just a variable. And this series comes from something else that is going on in that paper. And he sat down and computed several values of this tau of n, and then he again, typical Ramanujan style, he makes these leaps of faith based on computations that only he can do. And he made 3 guesses about this function tau of n, that it's multiplicative and what was it? And especially the tau of a prime p is of the order p to the 11 by 2. Now, this looks kind of bizarre to begin with. Tau of a prime, tau of 5 is roughly 5 to the 11 by 2. Why 11? Where is that coming from? Turns out, and this is something that Professor Ramanujan was mentioning, almost everything he touched was a tip of an iceberg. So this particular conjecture of Ramanujan, and if you look at that paper, he kind of says it in a very innocuous way. It seems to be the case, or it seems highly probable that tau p is like this. Became a very famous conjecture in the world of modular forms and automorphic forms and modern number theory. This is one of the driving forces of modern number theory, automorphic number theory. This particular conjecture of Ramanujan was proved by Deleuze, in using very, very fancy algebraic geometry technology. And Deleuze got a Fields Medal in 1978 for that work. So you see, somehow he picked on just the right thing, and this is not an accident. It could not be an accident because he just picked the right thing. And there's so many examples. It is coming out of a lot of labor, and then somehow his genius just picks on the one thing to study and the right observations to make, and it has just exploded. A lot of modern mathematics depends on that example of Ramanujan. It's just, to me, it's one of the most amazing things he's done.
Very, very interesting. I'll move on to Ramanujan. What's your pick?
Yeah, I want to pick something that is actually from his very early life. He, in Indian Mathematical Society, before Ramanujan went to England, he used to write. And there is a question 464 on which Ramanujan writes. And these are called equations of, the Ramanujan-Nagel equations, basically of the form x squared plus d equals a b power n, where you fix the dab and then the variable is x. And the beauty is that to show that the number of solutions in each case is finite.
Okay.
And, this is the sort of thing, again, something that a school child can act. A quadratic equation, come on, right? And you're just varying some parameters and you're trying to find how many solutions. It's something that a school child can think about, but it's remarkably deep. And, even if you put values like for 2, what happens, for 3, it leads to really beautiful mathematics. And I think Ramanujan worked on this as a teenager, right? And he was writing about these and talking about this. And he wrote these questions in Indian Mathematical Society foreshadow the kind of mathematics to come. But I think it's so simple, amazingly simple and beautiful. Unlike his huge, those equations with large numbers, factorial, c power, continued fractions, some incredible things that you can't even approach. This is something that I find.
So this leads me to a next question, Professor Ramanujan. This leads me to a next question that, see, if you look at many of his work, for most people, it will look like esoteric, purely maths for just sake of maths. Application. Do we really see that Ramanujan's work have played an important role in our contemporary life? In various areas of technology or other things. Professor Ramanujan?
Yeah, surprisingly, yes, and it has been so all along. And it's rather interestingly, Hardy was Ramanujan's mentor and co-author, claimed that the great thing about mathematics, especially number theory, is that it's completely useless. And unfortunately, that's not true, or fortunately, whatever. But for Hardy, that was very important as a pacifist to say that this kind of beautiful mathematics cannot be used for war. I think he was wrong, but anyway. But then Ramanujan was innocent of all applications, right? I mean, he had no idea of anything but mathematics pure form. But what is amazing is the depth of applications that it has seen. I already mentioned the areas like computer science, cryptography today. There are like many, many areas of computer science where you see Ramanujan graphs now playing a major role, complexity theory that you see. So there are many. And then in physics, there has been a tradition of applications of Rogers Ramanujan identities. Recently, we have heard about black holes, coupled black holes, and quantum theory. And this is something that Ashish Dabolkar from MIT was talking about in research in the last few years. And in fact, in the Ramanujan Yatra series, we had Zagier talk about work which has recently found application in quantum physics, and then in crystallography. So areas, and so this is some, but this is about mathematics, I would say.
Okay.
I mean, it's not just Ramanujan's mathematics, but whenever there is mathematics of sufficient depth, it finds its applications. I mean, it'll, and for all those who say that you must do things which have direct impact and direct relevance in technology, it's good to bear in mind that all this kind of mathematics is thought of as a pure game, but finds its applications 100 years after the man is dead, right? And people like Ono are finding applications within mathematics even now.
So that's very interesting, Professor Ramanujam, that how even after 100 years, Ramanujam's mathematics is used for developing new technologies or providing models, mathematical models for understanding physical phenomena like black hole. That's very interesting. Let me move to Professor Raghuram. The question that I would like to ask you is that even today, I'm told that people are going back to Ramanujam's work, and new areas of mathematics are emerging. Please throw some light on that.
I would like to provide one little example. There's a very small example, not to mention that I am doing something with Ramanujan's work, but while preparing for this discussion session, I pulled out my copies of Ramanujan's notebook, and if you look at the very last entry of what was, I think, his notebook 3, well, maybe his last but one entry, is some really amazing thing. So he writes down a certain number, e to the pi times the square root of 22. Okay, let me just say that again. E to the power pi times the square root of 22, and he writes it out. It is a 7-digit number. It's essentially an integer, 0.999 something. And he does it for 3 of these other things. He also does e to the pi times the square root of 58, is 11-digit number followed dot decimal, then 99999. So it's very close to an integer. You see, again, this is the simplistic originality that strikes you about Ramanujan. And now look at this, and this immediately in my mind triggers projects that students can, there's an algebraic number theoretic way of thinking about this. But you see, this came after the fact. In Raman, I don't know why he even wrote it.
I often tell that if Ramanujan had lived in these days of mobile numbers, he would have identified most mobile numbers with some formulas and so on.
Yeah. So I think it was said of him that every positive integer was a little friend of Ramanujan.
I know that. Yeah.
So you see, I just go to his notebook based on my whatever little I know mathematics. Some things catch my attention, and then this might lead to, well, in this case, I don't know if it will lead to anything, but I can have some students just study this, try to understand, and then they can progress in their research. So this is the way of mathematics, and somehow his notebooks and his papers are really a treasure trove. I think there's just gems and nugget beauty there.
Very, very interesting that how you both explained that even after 100 years of his death, Ramanujam's work still is a legacy. Now let me get into that legacy part and maybe perhaps some lessons from his life. So let me start with Dr. Ramanujam. that what do you think is one important message that we get from Ramanujan's life? If I ask you that, what would you put that as?
I think messages for teachers in particular, that you should always listen to what children think. We forget very often, and there may be thoughts, there may be ideas that as teachers we normally don't always listen. So it's a reminder. Another is, I think it's been mentioned earlier, that the tremendous amount of hard work that goes into any work. And it's also the case that by dwelling deeply, in thought, right, and working hard within disciplines, you could achieve something that is otherwise unimaginable. I mean, that is these are things that come through. And I again go back to what I said in the beginning about Ramanujan's life carrying another message that he came from great poverty, right? That there are all around students, children, people struggling with adversity and overcoming that by extremely hard work. Looking out for that is something that we often forget. And,
very, very important point. Perhaps I'll now move to Professor Raghuram. So, what would be your view, or what would be the lesson that you learn or you would like to highlight from Ramanujan's life?
Well, I think Professor Ramanujan has articulated it very well. Maybe I can just add one more thing, which is for young students dreaming of mathematics and being maybe inspired by Ramanujan's life. One of the take-home messages is if you like something, you just do it. You just do it. You just do it maybe to the exclusion of everything else. It is not a recommended way of studying, because Ramanujan also failed in some subjects, and luckily he was just so impossibly good with what he did. These other aspects ultimately had no effect on his mathematics. This may not be the case for every student, but nevertheless, if you like something, you just go for it and you do it wholeheartedly, completely, passionately, immersed in it 24/7. And I think that's what the hard work. Maybe for Ramanujan, it was not even hard work. That was just his way of life. That was what he was just so immersed in it. Hard work has a certain maybe negative connotation that you're kind of sweating it out and so on. I mean, if you're just completely in the flow, it may not even feel like hard work.
I've also read it. But I think, what Professor Raghuram said really needs underlining, I think, for the education system also, what we call failure. Because we know how much this affected Ramanujan, from his letters, from his, it sounds a little strange looking back, looking at Ramanujan's tremendous achievements, how deeply he was bothered by the fact that he could not get a degree, right, from University of Madras. Right? But it did bother him. It did bother him deeply. It affected him.
When the Madras University gave him a scholarship to go to Cambridge, the sum was to him, to Ramanujan, was substantial. So Ramanujan said that I'll give this much amount for me, and then he wrote to his mother saying that you keep this much amount for yourself, and he said that remaining money, please give it as scholarship to students who are needy in Madras University. After all, he was still living in poverty. I mean, it's not like he was living in a princely life. But even then, he thought that the scholarship that he got, he should give a part of it to other needy people. Even as human being, he was a very wonderful person. I think is also an important point to remember in this 100th year of his death anniversary. For want of time, we may have to end our conversation here. We have had a very wonderful conversation going about his mathematics, his work, his impact, his legacy, his life. And thanks to Professor Ramanujan, and thanks to Professor Raghuram for being in the show. Thank you all.
Thank you.
Thank you. Thank you.